Hello and welcome to RF Design Tutorials. This is tutorial 20 on mitigating the impedance mismatch distortion due to SMD mount pads in RF microwave and high-speed digital design. Here is the agenda for this video. We will look at how to calculate impedance using CILD, which is Control Impedance Line Designer, a very useful utility inside ADS while you are dealing with multilayer PCB, module, or high-speed design. We will then look at how to isolate the effect of the SMD pad in an interconnect design, and finally look at techniques to mitigate the impedance mismatch distortion to achieve as transparent interconnect design as possible, whether you are in RF microwave design application or designing high-speed digital boards, which are inherently a very broadband designs. It's a pretty interesting topic. Hopefully you will stay till the end of this video, and next few minutes will be very useful for your applications. Now, before we start, subscribe to my channel. Once you subscribe, don't forget to hit the bell icon to enable all the notifications. And after you watch the video, give it a thumbs up and share it with your friends and colleagues who may be interested in watching similar tutorial. All right, so let's go ahead and understand each of these topics, and they are going to be very useful in practical design applications. Now, let's look at the reference line which I have drawn. So in this particular application, I have a 6-layer stack up on which I wish to design an interconnect on CON layer. And due to nature of my board design, I need to insert a SMD component, which most of you will end up doing, whether you are doing high-speed serial link design or practical RF microwave designs. Right. So how do we go about this first? So while we are in the StackUp editor, you can notice there is an icon here called Control Impedance Line Designer. Now this is like a new age line calc tool which allows you to calculate the impedances depending upon various stack-up, no matter which layer you may be working upon. And you can define where is your return path. So in this case, you can see I have defined the signal to be con, the bottom plane or the return path to be on M2 layer, which is the second layer in my stack-up. And I'm using a microstrip single-ended configuration. However, you have choice of other topologies if you want to use them. Now in this application, I would like to calculate the 50 ohm line. And here I have done some pre-calculations. So I know at 10 gigahertz, which is supposed to be my highest frequency for this particular application, I would like to compute how much of this width will represent the impedance. So while we are in analyze mode, I can go ahead and launch analysis. Now this tool will analyze using the EM formulations in the backend, the impedance and rest of the parameters as subjected to find for my transmission line design. So it is clearly indicating a width of 0.226 mm line on CON layer, while you are referencing the ground plane to be on M2 will give you a 50 ohm line impedance. And per mm loss, which you can expect is around 0.025 mm. Okay, so these are the figure of merits you just remember. Now, in my layout, I have designed 1 mm, 1 mm, 1 mm. So I have drawn this, 0.226 mm, wide line, and this is a 3 mm long line. So with the 3 mm long line, if we go back to our line calculator and we just enter 3 mm and analyze and just look at the attenuation, so it should be around 0.075 dB, which we expect. Now, in order to set it up for simulation, I have connected two ports on either end of this line. And under port setup, I have declared the calibration type as TML instead of auto, which is by default there. So TML is a fully calibrated port. So essentially, if this line acting as a perfect 50 ohm line, you can see a 50 ohm getting connected to 50 ohm. So I should get a pretty good return loss and the insertion loss as predicted by my line calculator. And for rest of the board design, so if I make all the layers visible, You can notice in 3D, if I press 3, I have solid ground planes below this ground line, and this yellow color, which is basically M2 layer, is acting as a return path to my signals on the con layer. Now, how is it acting as a return path? In the port setup, remember, I have defined the ground layer to be M2. So when the EM excitation happens, the plus pin or the P1 will be placed on con layer and the return path will be on M2 layer. So I don't need to explicitly place any negative pin to define the return path. So pretty simple. And I have already covered some of these in my previous videos. Now when we perform simulation, it will take few seconds, and I'm using momentum RF mode in the EM setup because a small section of line. So RF mode will be quite fast and it will give me pretty accurate result because my layout section is pretty small as compared to the maximum frequency I'm simulating. Now here you can see, as expected, the return loss of the line is better than minus 30 dB, close to minus 38 dB, and which is representing a perfect 50 ohm line. Also, the loss, if you observe, is very close to what we expected from the line calculators. At 10 gigahertz is around 0.08 dB. So everything is working as we expected, as a nice clean 50 ohm transmission line design. Now, why I created, this line into three sections. So this is my input 50 ohm line. That's my output 50 ohm line. And this is the place where I have to mount an SMD device. And I would like to model the pad of that SMD to mount SMD. So let's look at that layout here. So let's go back to our ADS main window. And here is my simple setup where I do have input 50 ohm line, output 50 ohm line, and here is my SMD component. Now to model this effect of this SMD, I need to connect two ports, one at the input of the pad, one is the output of the pad, or you can connect it at the center of this pad depending upon where you want the connection definition to be. In my port setup, because I would like to see results directly using momentum instead of going into EM circuit co-simulation and connect a 0 ohm resistor or 0 ohm component to see the overall transmission. See the technique which I have used here. So pin 3 and pin 4, I have assembled them as a port, and between those port, I have defined the reference impedance to be 0.001 ohm. I could have defined 0 ohm, but defining 0 ohm is not a good practice. So I just put in 1 milliohm, kind of impedance between these. So that means during EM simulation, these two ports will be shorted with a 1 milliohm resistor. At the end of simulation, when I look at S21, which is basically going to represent connection from the input port to output port, it will give me the transmission response, and it will have the mismatch due to this wide line. So let's go ahead and perform a quick simulation. And again, during this simulation, the reference plane is also M2. As you can see, M2 is a solid ground plane. And as per my port setup, M2 is going to be my ground layer for port 1 and 2. For 3, it's not applicable because I have a resistance inserted between these two ports, which is 1 milliohm. Now, if we look at the performance of that line, let's start with return loss. You can see the return loss has become very poor. The blue curve here is representing the ideal 50 ohm line or a perfect 50 ohm line which we just simulated. Now if you compare the return loss, which is represented by this red trace, with SMD pad, as expected the return loss has distorted due to the wide line in between, a wide pad in between. Also, the insertion loss, which was close to 0.08 dB at 10 gigahertz, has increased to minus 0.7 dB, which is quite high. So if you are doing a good wideband interconnect design, this much loss by such a small portion of pad is not expected. It's going to deteriorate my overall system performance if I'm going to contribute to 0.7 dB of loss just by an SMD pad. So that's a lot of your useful power getting wastage here. Now, why is that happening? Well, we all understand by theory that wide transmission line are going to be a low impedance line, obviously. So your 50 ohm line is getting meshed with a low impedance line. So you will have reflection at that point. You will have reflection at that point, and that's where the energy is getting lost. Hence, you are having a higher insertion loss. Also in the Smith chart, as you can see, at the lower frequency, your line is close to 50 ohm, and that's what you also see in the return loss. So at the lower end of the frequency, your return loss is pretty good. But as soon as you move up the frequency, let's say you move till 10 gigahertz, the impedance shown is around 20 ohm or 22 ohm, and that is why your return loss is becoming poor, right? So it's very, very fundamental to RF microwave. Now, if we go and go back to this layout and click on this pad, we can see this pad is 1 mm wide pad. So how much impedance do we expect this pad to give us? So let's go back to our CILD. Now in CILD, let's enter 1 mm as the width. And with that 1 mm width, I'm interested to see what kind of impedance does it offer when my reference plane is on M2 layer, right? So let's go ahead and analyze. So now you will realize how cool is the CILD feature if you're dealing with multi-layer boards or high-speed digital application. Now we can see with 1 mm line, when my signal is on CON and return path is on M2, the impedance offered is around 17.6 ohm. Now when you combine with 50 ohm, 17.6 ohm, and 50 ohm, it's like a series combination. Overall, you will end up getting around 22 ohm. So that's the overall S11 seen by this, seen, produced by line at port number 1. So that's the problem. Now we need to improve this performance so that we can get this interconnect to be as transparent as possible. So what are the techniques we can use to achieve that? So let's go to cell number 2 layout. So in this cell layout, we have the same structure on CON layer, except that instead of having a full solid ground plane, I created a slot in M2 layer. Now, how do we create this slot? Well, I simply used a Boolean logical function to create the slot, and I have explained all these techniques already in my defected ground structure video. So if you haven't watched this video, please go ahead and watch a DGS design video. So you can either create this by using Boolean operation or simply use the derived layer concept, by which manipulating, let's say, the silk screen section here, the EM simulator will keep on doing this Boolean operation behind the scene when you perform the EM simulation. But in this case, I have used the Boolean operation. Now with this slot, what happens, the return path in this wide impedance line section is going to get shifted on this M3 layer. Now M3 is a full solid ground plane. So now the current or the return path will be on M3 layer. So if you look at the stack up again, so instead of referencing it to M2 layer, we are going to reference it to M3 layer, which is 5 plus 5, 10 mil far. Now, by your RF microwave theory, when you create the increased separation between your signal plane and the return path, the same width of line will now produce little higher impedance. Right? So we can go and check in CILD. Now if I switch the return path to M3 layer, the same 1 mm line which earlier was giving me 17.6 mm, if we go and analyze it, now you will see higher number here. So now it is going to give you 32 ohm of impedance. That means if I create the slot and perform the simulation again, which I'm going to do now. So in cell 2, if we go ahead and run an EM simulation, I would expect a better return loss compared to what I achieved earlier when I was using M2 as my return path. So let's give it a few seconds and the simulation will finish to, to verify our calculation or how things work in RF microwave or high-speed digital design. So here you can see the return loss, and the red color is representing the current return loss, and that has improved to minus 13 dB as compared to minus 8 dB, which was earlier. But still, we are very far from achieving a good 50 ohm match. Also, because of improved return loss, your insertion loss has improved. So instead of having minus zero point 0.7 dB loss, now you are getting minus 0.3 dB loss. But still, you are much higher. You're almost 4 times than what was given by the 50 ohm line. But the concept works. Now let's go back to our CILD. And what if we shift the reference to M4 layer? And with the same amount of width, if we go ahead and run, let's see what this 32 ohm becomes. Now this 32 ohm becomes 43. So obviously if we go back, and that's where I have my cell 3 design. In cell 3 design, I have also applied the slot in M3 layer, as you can see. And now the section or the SMD pad is going to refer to M4 layer, which is solid. Now, if we go ahead and run simulation on this layout, obviously the performance will improve. But now, beyond a point, the performance improvement will not be that high. In last case, what we observed, originally when we started with minus 8 dB, when we reference the ground to M3 layer, the performance got improved by 5 dB in terms of return loss, and also insertion loss almost halved at around 10 dB. Now with the current case, when we are using M4 as my return path, you can see from minus zero point 0.3, the insertion loss only improves to around 0.23. So it is not as dramatic as what we saw earlier. And also from minus 13 dB return loss, we only improved to something like minus 14.6 dB only. So it is again not as dramatic as 5 dB improvement. Now again, we can keep calculating and eventually we can find out where we are going to get good response. Now if we go to M5 layer and we analyze the same amount of width, what you will notice, we will reach very close to 50 ohm impedance as we are expecting. So it's 52 ohm. But now if we go and analyze that structure, which is cell 4, in cell 4, I have created a slot even in M4. You can see this M4 is the slot. And now it is referencing the ground to M5 as we just calculated in our CILD. So here we hope that this section is giving us 50 ohm, the preceding line and the line next to it is already 50 ohm. So what do you expect? You expect a pretty good response, right? Because all 50 ohm sections are getting cascaded. However, if you compare the performance from minus zero point 0.3 minus 0.23 dB, you only improve to something like minus 0.22 dB. So it is not as dramatic as we hoped for. Also, if you look at cell 4 results, the return loss only improved to minus 15 dB. So what's going on? Because as per CILD, this section should produce 52 ohm. The lines are already 50 ohm. So overall, you should have got 50 ohm. But here is the trick, right? So the slot which you created is exactly equal to the pad which you have. So that means you don't have the fields, fringing effect taken into account. So you're truncating the field right at the component pad. However, if we provide a little bit of space, and that's what we call as bigger slot in my design context. So I increase the size of the slot a little bit more around this, pad area. And if you go and simulate this particular design, we will achieve our objective because now the fields have sufficient place, to to distribute along this capacitive region or the low impedance kind of region, and now we would be able to fulfill the criteria which we are looking at. So here is the response and the final performance comparison. Now you can see the blue and the black curve. The blue curve is representing cell 5 with a slightly bigger slot. And you can see indeed we have achieved our objective. Now the insertion loss is exactly similar to what was predicted by a normal 50 ohm line. Also, the written loss of cell 5 is equal to what was predicted by a 50 ohm line. Also on a Smith chart, if you see, the red curve is where we started with, and these two dots are basically representing the reference line and the cell 5 design with a bigger slot. Now this particular design I can take and employ in my bigger board, because there's no point analyzing the whole big complex board. We can just analyze a small section, optimize the performance, and now this can set a good guideline for my PCB or board designer, and an RF microwave or a digital designer or digital engineer can give this guideline over to the layout guy to produce a layout with this particular constraint or with this particular guideline. And then when you receive the final board, when you analyze the board, you will, most probably don't need to tweak anything in that board design aspect. You will get performance pretty much in a single, operation or a single simulation run. Well, that's all for this video. I hope you find the content presented to be useful for your design work. Then you would be able to try it out on your own side and employ it in your design activities. Thanks again for all the attention and wish you all the best with your design work. Don't forget to give it a thumbs up and share it with your friends and colleagues who may be interested in watching this kind of tutorial. Thanks again and have a great designing phase.